This research paper presents a retrieval-augmented generation, or RAG-based, multi-agent large language model system designed to enhance natural hazard resilience and adaptation. The system aims to help decision-makers address challenges from extreme events like wildfires, floods, and hurricanes by providing accurate, context-specific information. At its core, the approach combines the strengths of large language models, or LLMs, with specialized data retrieval to overcome the limitations of general-purpose AI in handling domain-specific knowledge. The authors, a team from institutions including the University of Pennsylvania and Argonne National Laboratory, introduce WildfireGPT as a proof-of-concept application focused specifically on wildfire hazards. This system uses a user-centered, multi-agent design, meaning it involves multiple AI agents working together to deliver tailored insights for different stakeholders, such as urban planners, emergency managers, and infrastructure operators. By integrating data from natural hazard projections, observational datasets, and scientific literature, the RAG framework ensures that responses are not only generated quickly but also grounded in reliable, up-to-date information, making them more accurate and relevant than standard LLMs. In the introduction, the paper highlights how natural hazards are becoming more frequent and severe due to climate change, disrupting critical infrastructure and posing management challenges. It points out that while scientific research offers solutions, the sheer volume and complexity of this information often prevent it from being effectively applied in real-world scenarios. For instance, professionals in the field might struggle to access or interpret the latest studies on risk reduction. Here, LLMs emerge as a promising tool because they can process vast amounts of text, synthesize it, and communicate it conversationally, making scientific knowledge more accessible to non-experts. The paper builds on recent advancements in AI for hazard management. It references systems like Disaster Response GPT, which generates action plans for disaster scenarios, and evaluations of LLMs in fire engineering for tasks like structural design and prevention. Other examples include multi-round prompting techniques that allow users to refine responses iteratively, as well as specialized tools like ChatClimate and Climate GPT. These integrate data from sources such as IPCC reports and climate models to improve contextual understanding. In flood risk management, similar approaches have incorporated geospatial and demographic data. Commercial tools like Perplexity AI also play a role by retrieving and synthesizing current literature. Turning to the proposed system, the architecture of WildfireGPT is multi-agent, meaning it employs several interconnected LLMs or AI components that collaborate. One agent might handle user queries, another retrieve relevant data from databases, and yet another generate synthesized responses. The RAG component is key here. It retrieves specific information from trusted sources before generating answers, reducing the risk of hallucinations or inaccuracies that plague standalone LLMs. For example, when a user asks about wildfire risks in a particular region, the system pulls in projection data, historical observations, and scientific papers to craft a response that's both comprehensive and evidence-based. The paper evaluates this system through 10 expert-led case studies, comparing it to existing LLM-based solutions. Results show that WildfireGPT significantly outperforms these alternatives in providing decision support. It delivers more precise risk insights, better handles complex queries, and adapts to the needs of diverse stakeholders. This superior performance stems from the integration of high-quality data sources, which ensures the system's outputs are not only informative but also actionable for real-world applications. In terms of implementation, the authors emphasize a user-centered approach. This means the system is designed with end users in mind, featuring intuitive interfaces for querying and interacting with the AI. For instance, stakeholders can input specific scenarios, like assessing wildfire vulnerability for a city's infrastructure, and receive tailored recommendations. The multi-agent setup allows for dynamic collaboration, where agents can cross-reference information or escalate queries to more specialized modules if needed. The broader implications of this work extend beyond wildfires to other natural hazards. By demonstrating how RAG-based systems can bridge the gap between scientific research and practical application, the paper suggests potential for scaling this model to areas like flood or hurricane management. It underscores the transformative role of AI in democratizing access to knowledge, enabling faster decision-making in the face of climate-driven risks. Technically, the system leverages advancements in natural language processing to handle the nuances of hazard-related data. For example, it processes textual information from sources like observational datasets and literature, then uses generation techniques to produce clear, conversational outputs. The authors also address ethical considerations, such as ensuring data accuracy and avoiding biases in AI responses, which is crucial for high-stakes applications like disaster planning. Overall, this research contributes to the growing field of AI for environmental resilience by offering a robust framework that combines AI's generative capabilities with reliable data retrieval. It paves the way for more effective tools that can support policymakers, scientists, and communities in adapting to an increasingly hazardous world.